Movement is the eternal melody of the universe. At every moment, all things in the universe are in some kind of moving state, whether as large as a galaxy or as small as an electron. As we know, the Earth revolves around the Sun, and the Sun revolves around the center of the Milky Way. Obviously, the Milky Way should also be in some kind of moving state. So how does the Milky Way move in the universe? Scientists have long answered this question. The Milky Way is racing through the universe at a speed of 600 kilometers per second. How is the speed of the Milky Way defined? In order to describe the movement of the Milky Way, we first need to choose a suitable reference object, and the criteria for this suitable should be that the reference object can be universally applied to all celestial bodies in the universe. So is there such a reference object that meets this standard in the universe? Yes. It is the cosmic microwave background radiation. Simply put, the cosmic microwave background radiation can be considered as the electromagnetic radiation left over from the beginning of the universe. They are also called the oldest light in the universe. Since the speed of light is limited, these ancient photons are still propagating in the universe until now. They are uniformly distributed in the cosmic space, and the many celestial bodies in the universe are also traveling in the sea of photons of the cosmic microwave background radiation, including the Earth. Due to the movement of the Earth, we observe slight changes in the cosmic microwave background radiation, specifically manifested as the wavelength being slightly shorter in the direction consistent with the direction of the Earth's motion, which is also called blue shift, and slightly longer in the opposite direction, which is called red shift. Through observation and analysis of this phenomenon, scientists have concluded that, relative to the cosmic microwave background radiation, the Earth's velocity is about 368 km/s, and the direction of this velocity is almost completely opposite to the current direction of the solar system revolving around the galactic center. Scientists believe that the reason for this phenomenon is that the velocity of the Milky Way in the universe is faster than the orbital velocity of the solar system, and its direction is opposite to the current direction of the solar system's orbital motion. To facilitate understanding, let's illustrate with an example. Suppose a train is traveling from east to west, and a person on the train is running from west to east. According to the person's observation, although his own direction of motion is from west to east, his direction of motion relative to the ground is from east to west. Why is this? A simple answer is that the train is faster than his own speed and the direction is opposite. Now it is known that the person's speed is 5 meters per second. Direction is from west to east, and according to his observation, his speed relative to the ground is 95 meters per second. Direction is from east to west. Can we calculate the train's speed relative to the ground? The answer is definitely yes, because the speed of the train relative to the ground is actually equal to the person's speed relative to the ground, plus his own speed, which is 100 meters per second. If we replace the train with the Milky Way, the person running on the train with the solar system, and the ground with the cosmic microwave background radiation, we can clearly understand the relationship between the orbital motion of the solar system and the motion of the Milky Way relative to the cosmic microwave background radiation. Since the Earth is just a planet in the solar system, it can be considered that the Earth's velocity relative to the cosmic microwave background radiation is actually the velocity of the solar system relative to the cosmic microwave background radiation. So we can conclude that the velocity of the Milky Way relative to the cosmic microwave background radiation is actually equal to the velocity of the Earth relative to the cosmic microwave background radiation, which is 368 km/s, plus the orbital velocity of the solar system. Observational data shows that the orbital velocity of the solar system is between 208 km/s and 237 km/s. Accordingly, it can be calculated that the velocity of the Milky Way relative to the cosmic microwave background radiation should be between 576 km/s and 605 km/s. Considering measurement errors, it is generally taken as 600 km/s. Since the Milky Way is racing through the universe at high speed, where is it taking us? Scientists speculate that the reason why the Milky Way is in this moving state should be the effect of a powerful gravitational source. People then called this gravitational source the Great Attractor. Unfortunately, the Great Attractor is located in the direction of Hydra and Centaurus, and this area is blocked by the galactic disk of the Milky Way, so research in this area had been stalled for a long time. It was not until the development of observation techniques based on radio waves and X-rays that scientists were able to continue in-depth research on the Great Attractor. The results show that the distance between us and the Great Attractor is between 150 and 250 million light-years. Its gravity is so strong that millions of galaxies are affected by its gravity, with an impact range of hundreds of millions of light-years. That is to say, the Great Attractor is the destination of the Milky Way. It is taking us there at a speed of 600 kilometers per second. So what exactly is this Great Attractor? In fact, the scientific community currently does not have a definitive answer and can only make some reasonable guesses. A more widely accepted view is that the Great Attractor should be the gravitational center of the Laniakea supercluster to which the Milky Way belongs. In addition, some nearby large structures also provide additional gravity, such as the Shapley supercluster, which is about 650 million light-years away from us and is located behind the Great Attractor. Will the Milky Way eventually be swallowed up by the Great Attractor? The answer is no. We should know that the universe is in a state of continuous expansion, which will cause those distant celestial bodies in our view to move away from us. This speed of moving away from us due to the expansion of the universe is also called the recession velocity. The farther away, the faster the recession velocity. The essence of recession velocity is the apparent velocity caused by the expansion of the universe. It is not the real motion velocity of the celestial body in cosmic space. Please distinguish between them. Observational data shows that for every increase of 10 million light-years, about 32.6 million light-years, between 2 points in cosmic space, the speed at which they move away from each other due to the expansion of the universe will increase by about 67.8 km/s. In this case, even if we calculate based on the closest distance between us and the Great Attractor, which is 150 million light-years, its recession velocity is as high as 3,200 km/s, which far exceeds the approaching speed of the Milky Way to the Great Attractor, that is 600 km/s. This means that although the Milky Way is rushing towards the Great Attractor, it can never reach its destination. With the continuous expansion of the universe, the distance between the Milky Way and the Great Attractor is actually increasing. That's all for today. Thank you for watching. See you next time.